Imagine trying to prove, mathematical theorems, but automatically. Like that's what we're diving into today. This really cutting edge research that's combining artificial intelligence and like good old fashioned mathematical logic.
Yeah, it's a fascinating area.
It really is.
Where researchers are really kind of pushing the boundaries of what AI can do.
Right. And we'll be looking at excerpts from a research paper titled Learning Conjecturing from Scratch, where researchers trained an AI system to help prove these tricky mathematical statements, specifically about integer sequences from the OEIS,
right?
The Online Encyclopedia of Integer Sequences.
Yes.
Which is basically just this giant database of cool number patterns.
It is quite the treasure trove if you're interested in number pattern.
Yeah. And think of this deep dive as like a shortcut to understanding how this AI learns, what kind of problems it can solve, and why it's such a big deal for programmers, data scientists, or anyone who just loves a good brain teaser.
Right. Yeah, the OEIS is it's a vast and constantly growing collection of these integer sequences. Yeah. Each with descriptions and formulas that kind of reveal these hidden patterns within them.
Yeah. And the challenge the researchers tackled is proving that different formulas or algorithms for the same OEIS sequence actually produce the same results.
Right.
This might sound straightforward, but
yeah,
when you add in the concept of induction, it gets a lot more interesting.
Induction is, it's a fundamental proof technique in mathematics, essentially. Yeah. You prove something is true for all cases by first showing it's true for like a base case, and then demonstrating that if it's true for one case, it must also be true for the next.
So to make this super concrete, let's look at an example from the OEIS, sequence A217. The triangular numbers.
Excellent example.
Yeah.
Triangular numbers, those are a classic.
Right.
You can calculate them using a simple formula, n times n plus 1 divided by 2. But you can also express them as a summation, 1 plus 2 plus 3, and so on, up to n, proving that these two methods are always equivalent. That's where the induction comes in.
Exactly. It's this kind of problem that the researchers train their AI to solve. Now, here's where it gets really interesting. This AI system builds upon their previous research, where they were generating programs to compute these OEIS sequences.
Right.
But now they've shifted gears.
Now the focus is on generating predicates.
Okay.
Predicates are essentially logical statements that can be used as part of inductive proofs. They're the building blocks for constructing those complex mathematical arguments.
Inventing predicates, that sounds incredibly difficult. How does the AI even begin to tackle that?
Yeah, you're right. It's a massive challenge. The space of possible predicates is enormous. It's like searching for a needle in an infinite haystack.
Right.
Plus, evaluating these predicates with an SMT solver, a kind of automated reasoning tool like Z3, takes time.
So they can't just test every possible predicate. They need some clever tricks to narrow down the search.
Exactly. They had to develop strategies to kind of manage this huge search space and find the most promising candidates.
Okay, so before we dive into those strategies, I'm curious about the language this AI uses. How does it represent these programs and predicates?
So the language is based on simple mathematical operations, addition, subtraction, multiplication, division, and a special construct called loop, which allows the AI to express the recursive nature of these integer sequences.
So it's like a shorthand for mathematical ideas.
Precisely. For example, the program loop, 2x(x1), generates powers of 2.
Okay.
Each step multiplies the previous result by 2, starting with 1.
Okay.
It's a really compact way to represent that sequence.
Okay, I think I'm following you.
Okay.
But to be honest, that's a lot to take in. Can we break that down a bit further, maybe with another example? Something that shows how this loop thing really works?
Sure. Let's look at another example. How about the sequence of Fibonacci numbers?
Okay.
Each number is the sum of the two preceding ones, starting with 0 and 1. So the sequence goes 0, 1, 1, 2, 3, 5, 8, and so on.
Fibonacci numbers classic.
Yeah.
So how would you write a program using this loop language to generate that sequence?
Good question. Here's how you could do it. Loop. X plus y, yx 1, 0. Let me break that down.
Okay.
The first part, x plus y, that's the rule for generating the next number, adding the previous two.
Okay.
Then yx tells the loop to shift the values along what was y becomes the new x, and so on. And finally, 1, 0, those are the starting values.
Okay, so it's like each step of the loop takes the previous two numbers, adds them together to get the next one, and then shifts everything over to get ready for the next iteration.
Yeah.
It's kind of elegant how it captures the essence of the Fibonacci sequence in such a compact way.
Exactly. And this is the kind of program that the AI can generate and manipulate. Now, going back to those strategies for finding predicates, remember, they can't test every single one.
Right, the infinite haystack problem.
Yeah.
So what do they do?
Well, initially they took a brute force approach. The system generated a vast number of predicates and then used clever filtering techniques to kind of weed out the ones that were obviously bad or redundant. One of their tricks involved this fingerprint technique, comparing how predicates evaluate on specific values to quickly identify duplicates.
Ah, so it's like checking if two recipes produce the same dish by tasting them without needing to know every single ingredient or step.
That's a great analogy, and this initial brute force approach gave them some valuable starting data, a collection of problems paired with predicates that help solve them.
The training data. This is where the machine learning magic comes in, right?
Exactly. They use a neural machine translation model, or NMT, and train it on these problem solution pairs. It learns to associate specific types of problems with the predicates that are likely to be helpful.
It's like the NMT is learning to speak the language of mathematical proofs by studying examples of successful proofs.
Yeah.
I'm curious, though, even with clever filtering, wouldn't some important functions or patterns be missed just because they don't show up often enough in the initial data? Like, how does the AI go beyond what it's already seen?
You're right. That's a key challenge to overcome this. They use data augmentation techniques, essentially giving the AI a broader range of experiences to learn from. One trick they use is shifting the indices of loop functions.
So it's like teaching the AI to recognize different dialects of the same mathematical language.
Precisely. And another technique called definition expansion involves rewriting predicates to include these helper functions. This makes them more complex, but potentially more powerful.
So it's like taking a simple sentence and adding more detail and nuance.
Exactly.
Yeah.
Now, here's where it gets really mind-blowing. This system doesn't just learn from the initial data, it continuously improves itself.
Hold on. This is like a mathematical perpetual motion machine. The AI is essentially bootstrapping its own learning, becoming smarter with every iteration.
That's a great way to put it. It uses the NMT to generate new predicates, test them with the Z3 solver, and if they work, adds them back into the training data for the next round. It's a beautiful example of a positive feedback loop in AI research.
Wow, I wouldn't have thought of that. It's
Well,
like the AI is thinking outside the box, even in the world of mathematics.
yeah.
So how well does it actually perform? Can it really solve these tricky problems from the OEIS?
So in their longest runs, the AI solved thousands of problems
Yeah.
from the OEIS benchmark.
That's impressive. It sounds like it's already outperforming traditional approaches.
It is to make sure they compared its performance with these existing automated theorem provers, specifically Z3 and CVC5,
Okay.
both known for handling induction and arithmetic reasoning. They even gave these provers a head start
Oh, wow.
by adding induction axioms manually.
Okay, so it's like a competition, this new AI system versus the established champion.
Exactly. And the AI consistently outperformed Z3 and CVC5 even when they got that extra help.
Wow, that's a pretty decisive victory, but can we get into some specifics? What kind of problems did it solve?
Absolutely. One example involved pentagonal pyramidal numbers. You know, the number of objects you can arrange in a pyramid with a pentagonal base. The AI had to prove that two different ways of calculating these numbers are equivalent.
Okay, so we got two formulas for the same thing, and we need to prove they always give the same answer. How did the AI tackle this?
It came up with a predicate that perfectly captured the relationship between the loop function used to calculate these numbers and the other parts of the formula. It basically said, hey, if this loop function is doing what it's supposed to, then these two ways of calculating pentagonal pyramidal numbers must be equivalent.
Okay.
And Z3 was able to use this predicate to construct a valid proof.
So the AI found the key insight that unlocked the whole proof. What other interesting solutions did it come up with?
There's one involving sequence A59826, which is related to summation. What's remarkable here is that a direct induction on the problem equality wouldn't work.
Wait, why not? Couldn't you just apply induction straightforwardly?
The relationship between the two sides of the equation was too complex for that. The AI had to come up with a more general lemma, a kind of stepping stone to bridge the gap.
It's like it invented a new tool to solve a particularly tricky problem.
Precisely. It's a beautiful example of how the system can go beyond simply applying known techniques. It can actually discover new mathematical relationships.
This AI is starting to sound like a real mathematical prodigy. Are there any other examples that showcase its ingenuity?
Oh, plenty. One cool example involves sequence H126, which consists of powers of 17. Now, there are a couple of ways to calculate powers of a number. You can use repeated multiplication, but there's also a faster way called exponentiation by squaring.
So we're comparing a brute force method to a more elegant and efficient one. Sounds like a classic computer science problem.
Exactly. And the AI was able to identify a predicate that captured the essence of exponentiation by squaring it. Notice that in the faster method, the number 17 is only calculated once and then stored for later use, which saves a lot of computation.
It's like the AI noticed a clever optimization trick and then used that insight to construct a proof.
You got it. Now, here's where things get even more interesting in one run. The number of problems solved suddenly jumped significantly.
Really?
This was due to the AI inventing a new predicate that puzzled the researchers at first.
A mathematical mystery. What was so strange about this predicate?
It involved a combination of loop functions and a specific arrangement of terms that didn't immediately seem relevant. It took some careful analysis to understand the logic behind it.
It's like the AI found a secret passage in the maze of mathematical reasoning.
Exactly. And this seemingly obscure predicate turned out to be incredibly powerful. It unlocked solutions to a whole bunch of problems that had previously stumped the system.
So the AI stumbled upon a hidden gem of mathematical insight that's incredible.
It really is, and this brings up a crucial point. Sometimes the most profound mathematical insights come from unexpected places.
So what made this master key predicate so special?
Its power lies in its generality. It captured a relationship between loop functions without referencing specific numbers or constants that varied from problem to problem.
So instead of being tied to a specific problem, it expressed a more abstract mathematical truth that held across multiple problems.
Precisely. It's like expressing the concept of area without specifying whether you're dealing with a square, circle, or triangle.
So it discovered a fundamental principle of mathematics rather than just a clever trick. This whole self-learning aspect is truly remarkable. It's like watching a mathematical prodigy grow and develop its skills.
And it makes you wonder what this means for the future of fields like software development and mathematical research.
Exactly. Imagine a world where AI can help us not only verify the correctness of complex software like self-driving cars,
Right.
but also collaborate with mathematicians to discover new theorems and push the boundaries of human knowledge. This research really opens up a whole new world of possibilities.
It does. This is just the beginning, and it's going to be fascinating to see where it leads.
Well, that wraps up our deep dive into the world of AI and mathematical proofs for our listeners. Here's something to ponder. If AI can now help prove theorems, what other intellectual feats might it accomplish in the future?
It's an exciting question to consider as we continue to explore the ever-evolving world of artificial intelligence.
Until next time, keep exploring, keep questioning, and keep diving deep.